If the outer boundary of a hydrogen atom, where the electron is found, were enlarged to be 2 miles wide, about the size of a city, the single proton in its nucleus would be the size of a golf ball. It's here we find elements at their most elemental, because every nucleus contains protons, and it's the number of protons that determines what kind of element the atom is. 1 proton is hydrogen. 2 protons, helium. 3 protons, lithium. 4 protons, beryllium, all the way up to element 118, with 118 protons. The number of protons is called the atomic number, and it's the fundamental organizing principle of every table of the elements, including this one.
Wow! This is cool. You have a periodic table.
Well, it's called a periodic table. Why do people keep putting them on the wall?
Every high school student has seen the elements chart, but author Theo Gray's version is unique. Handmade, with each element's identity card meticulously carved into the wood.
But I have to say I've never completely gotten it, right? They're filled with stats and figures that don't make any sense to an ordinary person.
Theo gives me a refresher.
You've got the name of the element. You've got the atomic symbol.
Ca for calcium.
You've got the atomic number, which is the number of protons in the nucleus of each atom of that element. It's probably the most important thing on this tile.
So where's gold?
Gold's right there, number 79.
Okay, so here's a classic example. They would do much better with marketing this table if the name and the symbol matched. Gold doesn't even have AU in it.
The symbol is based on the Latin name, aurum. And if you think about it, the name of each element is the least important piece of information you could possibly have. What matters about elements is that they are real physical substances with properties and things you can do with them.
Theo makes the point by putting me in touch with the real deal.
Oh, I see what you've done.
To make the entire table less abstract, he invites me to lay out the rest of his collection of pure elements.
Well, this is really pretty amazing. This is a visual representation of every single element that makes up this entire planet and everything on it.
Then, Theo reminds me of something I'd forgotten. As we can clearly see, more than 70% of the elements on the table are metals, shiny, malleable materials that conduct electricity.
There's sort of a diagonal line here. Everything from here on over, including the bottom part, is all metals. Everything from here on over is non-metals. And down the middle are these kind of halfway in-between things, which include, for example, semiconductors, like silicon.
Right. You know, I have to say, many of these elements look the way you would think. You know, gold looks like gold, silver looks like silver, but not all of them. The one I was looking at in particular is calcium. Most people probably think of calcium as white and chalky. You know, it's bone, it's chalk, it's milk. But this is a silver shiny metal.
This is when Theo's collection starts to get really interesting, when he pairs the pure elements with their more familiar forms, like pure calcium metal combined with other elements to make bone, bismuth in stomach medicine, bromine in soda, and even this element hiding out in collectible Fiesta ware. This bowl from the 1930s gets its orange color from uranium, and it's actually dangerously radioactive. Theo's table and his remarkable collection make a powerful point. From about 90 elements found on Earth, nature and man have derived millions of different substances that make our world. But to me, there's something even more amazing. The table organizes the elements by atomic number. That is, the number of protons in each atom. Yet the table's creator, a 19th century Russian chemistry professor named Dmitry Mendeleev, knew nothing about protons or atomic numbers. Even the atom itself hadn't been discovered. To understand how he cracked the code of the table, I've come to St. Petersburg, Russia, to the State University, and to Mendeleev's apartment and office. In the late 1860s, at this very desk, Mendeleev set out to discover the underlying order to the elements. In one often repeated story, Mendeleev is said to have created 63 cards, one for each of the elements known at the time. He distinguished them not by atomic number, but by atomic weight.
So he didn't know about atoms, but isn't this the atomic weight? How does he know the weight if he doesn't know about atoms?
Разумеется, взвешивать атом в граммах.
It's not in grams or pounds or kilograms. In the 19th century, they did it like this. They compared the weights of different elements to the lightest, hydrogen. So when they say oxygen is 16, that means 16 times the weight of hydrogen.
19th century scientists relied on relative weight to order the elements. Imagine if you have two containers, one full of red marbles, one full of blue marbles. If both contain the same number of marbles, but the blue container weighs twice as much, you can infer that the blue marbles weigh twice as much as the red marbles, even if you can't see the marbles at all. Early chemists devised clever ways of calculating the weights of elements, even gases, relative to the lightest one, hydrogen.
So the chemists knew that different elements have different weights, but why not just one big line forever?
Он будет располагать.
Mendeleev decided that he would arrange them by weight, but also by family.
This is one of Mendeleev's charts. You can see hydrogen sticking out just as it does today. The families he knew are now arranged in columns. This one has the metals, lithium, sodium, and potassium, that explode in water. Next door, calcium and magnesium, which also react with water. This big block in the middle are metals that are safe to handle, like nickel, iron, zinc, and gold. As we go to the right, the elements become less metallic. These columns are headed by boron, carbon, and nitrogen. In this neighborhood, some elements conduct electricity, some don't, and some can't make up their minds. But next door is a more volatile crowd, headed by oxygen and fluorine. The table gets its shape from the properties of the elements, like relative weight, conductivity, and reactivity. It's true today as it was in Mendeleev's time. Though his chart displayed only the 63 elements known at the time, his understanding of the family properties was so strong, he was able to leave gaps in his chart, bold predictions of elements yet to be discovered. And when they were eventually found, they proved completely consistent with his descriptions. Mendeleev lived until 1907, long enough to see 3 gaps filled by the discoveries of scandium, gallium, and germanium. Since his death, dozens of new elements have been discovered. And incredibly, his chart perfectly accommodates all of them, including an entire group that fits neatly onto the end of the table, the noble gases.
Where does that term noble gases come from? Are they nobility? Do they rush to rescue maidens?
No, you're thinking of heroes. They're like nobility in the sense that they don't mix with the riffraff. They don't like to react with any other elements. By and large, it's not possible to form compounds with them.
Well, it's a shame for your collection that they're gases, because you've got big blanks here. Oh.
The noble gases, like neon and argon, pose a problem for chemists who prefer their elements to join forces and react with each other. You can run an electric current through them, excite their electrons, and get pretty colors, which is how neon lights work. But the noble gases don't react. They pretty much refuse to combine with other elements.
Being an inert gas, being unwilling to mix with the other elements, react with them, this is a very clear-cut distinction that sets apart this particular column from all the others in the periodic table.